Hello, my name is Dr. Owen Lyne. I'm a Senior Lecturer in Statistics at the School of Mathematics, Statistics and Actuarial Science at the University of Kent. And in autumn 2020, I will be teaching the module MA351, Probability. So I'd like to talk to you a bit about that module for our Recharge Your Maths program and show you an example. So probability comes in two main areas: probability theory, the abstract theory that's not concerned with the details of particular systems, but talks about the laws of probability, the rules. How does probability work? And then there's applied probability, where we apply probability to specific systems. We try and model that behavior, understand how the system works, and to make predictions of its future behavior. And this module will look at both of those aspects of probability. What I want to talk to you about in this video is something called the birthday problem. It's a famous problem with a rather surprising answer. We can state the problem very simply. We have m people in a room. What's the probability P of m that at least two of them have the same birthday? So two of them have a birthday on April the 12th, say. And then the follow-up, how many people do we need to get a probability of at least half, so that it's more likely than not that some people in the room share a birthday? For probability questions that involve the words at least or at most, it's often easiest to work out the probability of the complementary event, the probability that the event doesn't happen. Because if I had 100 people in the room, I could have 5 people who were born on September the 7th. I could have 2 people born on August the 9th. I could have 3 people born on one day, 4 people born on a different day. There would be lots of combinations, lots of possibilities that I would need to count to work out this probability. What's much, much simpler to do is work out the probability that none of them have the same birthday, and therefore at least 2 of them do not share the same birthday. So we'll call that probability Q, and it depends on m, the number of people in the room. So let's see if we can calculate Q and what answers we get. So imagine the people walk into the room one at a time. We record their birthdays on a calendar. So I've done that at open days with prospective students to illustrate this problem. So the first person arrives, the calendar's blank, they tick their birthday, there's no chance they share it with anyone. So the probability that nobody matches is 1. Second person walks into the room, one day's already ticked off on the calendar, they've got 364 other days to choose from. Assume for this purposes we're not dealing with a leap year. So they've got 364 days to choose from. If we assume all the days are equally likely, the probability is then 364 over 365, which is 0.9973 for 4 decimal places. When m equals 3, the third person who comes in needs not to share a birthday with either of the previous 2, who must themselves have different birthdays. So I've still got 364 over 365, but now I multiply that by 363 over 365. The third person sees a calendar with 2 days ticked off. They've got 363 days left that they can choose from. And it's appropriate to multiply those 2 probabilities together if we believe these events are independent. There's no reason for one person's birthday to be related to somebody else's. That's an assumption that might break down. I had a school group who laughed at me when I did this problem because they knew they had a pair of twins in the room who definitely did share a birthday. But if we assume they're independent, and that's a concept we'll talk a lot more about in the module, this is the calculation we would do. We would multiply these 2 probabilities together, and then we would get 0.9918 before death. Okay, assume the first 3 people don't match. What about m equals 4? Fourth person needs not to share a birthday with any of the previous 3. So I have the same first 2 terms I had before. They have to have different birthdays. And then when they look at the calendar, 3 days are already gone. They've got 362 empty days left. So we multiply by that. And the probability is now 0.9836. So this probability is slowly going down. M equals 5. I had one more term, 361 over 365. And as you'll see, each time these fractions are slightly smaller, they'll make the expression smaller again and again. And at this point, that reduction is accelerating a little bit. So Q5 is 0.9729. This probability has gone down a little bit more each time. Now it's going to be quite tedious to calculate that all the way up to 365. But what we can do is spot a pattern in these mathematical expressions and create a general formula. And that's often the power of mathematics. It's something we'll use a lot in probability. Find a general formula so we don't have to work all of these out one by one. So if we have m people in the room, what's the pattern? The easiest thing to do is imagine that I have a 365 over 365 at the start of the expression. That corresponds to the probability 1 for Q1. Then we multiply by 364 over 365. Then 363 over 365. And we keep going for how long? Well, when Q equals 5, we went down from 365 to 361. We went down by 4. So we went down by m minus 1. So we've subtracted 365 minus m plus 1. So if you plug into that formula, you'll get all the values we've just had for Q1, 2, 3, 4, and 5. But this formula also works for larger values of m. Then in the denominator, we always have 365. So we have 365 to the power of m, when we've added that 365 at the front. Okay, I can use factorial notation to write that in a different way to avoid having this dot, dot, dot of multiplications. This looks like 365 factorial with the rest of the terms cancelled out, the terms that aren't there going down to 1. So if I did 365 factorial divided by 365 minus m factorial, that is what I would get left. So that's quite a nice way of writing this expression in a compact form. It's still quite slow to calculate, but it's now really easy to code a computer to calculate those results. And rather than look at them numerically, let's look at them graphically. I've used the computer package R, which we'll teach you in the module MA306, statistics. So here's my plot of QM. The probability there is no match with a number of people going from 1 to 365. And as you can see, to start with, that graph is going down quite slowly, but that accelerates. And then very quickly, it drops well below 0.5. It drops down to very close to 0, and then looks very flat after that. So on that graph, we see that the number of people we need that probability to be about a half is perhaps much smaller than we expected. We don't need 180 people. We don't need half the number of days in the year. This probability is much smaller than that. So let's try and zoom in on that graph to see what the answer to our problem is. So if I draw the graph only up to 100, then I get a much clearer view of what's happening. So here are the first few values we'd calculated, Q1, 2, 3, 4, and 5. And that decreases, that accelerates. And then it asymptotes again, it levels off at 0. The probability gets smaller every single time. One more person in the room makes it more likely we have a match, less likely that we don't have a match. So this function is always decreasing. It starts at 1 and it ends at 0. Once you have enough people in the room, all the days on the calendar will be used and the probability must ultimately be 0. If I zoom in a little bit more, I can see that by the time we get to 60, these probabilities are very, very small. And the probability of a half is somewhere between perhaps 20 and 30 people, a much smaller number than you might initially guess, you might initially think. So let's draw some more lines on that graph to help us see what's going on. So here's a horizontal line at p equals 0.5. So we can see the probabilities start above 0.5, they drop below 0.5 about here. So let's figure out what that point is. Let's draw another line on the graph. This is a vertical line at m equals 23. So we can see at 23, we have the first value, which is below the horizontal line. The first time this probability Q is less than 0.5 is when there are 23 people in the room. So the answer to the problem, how many people do I need in the room for a 50-50 chance that two of them share a birthday, is only 23 people. Here's my expression for the probability P that I do have a match. That's 1 minus Q. And so I can write it in this form. And surprisingly, we found that P is greater than a half whenever M is greater than or equal to 23. P of 23 is actually 0.507. By the time we have 50 people in the room, it's 0.970 to 3 decimal places. With 57 people, it's 0.990. So there's a 99% chance if you have 57 people in the room that you will have such a match. And when I've done this as an experiment with groups coming into an open day, I've sometimes had a match in as few as 10 people. Other times it's taken me about 55 people before I get a match. But I found that this works very effectively. We made lots of assumptions that all the days of the year were equally likely. In fact, if that wasn't true, we get matches even quicker. If some parts of the year are more common for birthdays, then we'll probably get a match in that period. So we've made various assumptions, but in fact, our conclusion is quite robust, even against those assumptions. So we'll look in a lot more detail in the module at some of the techniques we've used, the methods we've used to justify that. Thank you very much for your time watching this video, and I look forward to teaching you on MA351 probability.